Rational expressions, part 2. We're going to continue to simplify things with square roots. We use this property backward in the last section. In the last section, I started with something that might have been 15 times 6 with a square root and said you can write that as square root of 15 times square root of 6. You can use that in the opposite direction too. If you have square root of 15 times square root of 6, you can start by multiplying the 15 and the 6. I use my calculator. 15 times 6 happens to be 90. So now I have square root of 90, and now I want to try to simplify that. 90 is 9 times 10, and the square root of 9 happens to be a nice number. It's 3. The square root of 10 is not a nice number, so I leave it just like that. 3 square roots of 10. Alright, similar manner here. I grab my calculator and I do 12 times 30. That should be 360. 360, you can reduce it lots of ways, factor it lots of ways, but I think the best way is 36 times 10, because the square root of 36 happens to be a nice number. It's 6 square root of 10. The fact that we got 10 for both of these is just a happy coincidence. Don't expect that. Just the way it worked. Alright, now let's multiply some things where we have a couple binomials. 2, well, it's really just a monomial because it's just a number, but it looks like a binomial. 2 minus square root of 5, 2 plus square root of 5. You might notice this as a special formula we had before. Before we had a formula where we took a minus b times a plus b, and we noticed something special happened. The middle terms added up to 0. We ended up with a squared minus b squared. Same thing's going to happen here, but let's multiply it all the way out just to check it. 2 times 2 is 4. And then 2 times the square root of 5 is 2 square roots of 5. And then we have a minus 2 square roots of 5. And then a minus square root of 5 times square root of 5 is square root of 25. So this turns out to be 4. Those two add up to 0. Minus 5, square root of 25 is a nice number. That's minus 1. Alright, so using that same principle here to multiply these two, all I really have to do is multiply the fronts. 4 times 4 is 16, minus square root of 10 times 10 is 100. That's 16 minus 10, which is 6. And I think I said this before, but maybe not. There's actually a fancy name for something like this, where these two things are exactly the same, but one has a plus and one has a minus. The fancy name for these two things, these two pairs, are called conjugates. And I'll be using that word a bit later here in this section. Alright, the other thing that happens in this section is we talk about rationalizing the denominator. Rationalizing the denominator is fancy words for saying get rid of the square root on the bottom of the fraction. So if we have 3 divided by the square root of 5, we want to rationalize. If all you have is a single square root down on bottom, then you simply multiply top and bottom by that same square root. So up on top, I'm going to have 3 square roots of 5. Down on bottom, I'm going to have square root of 25. And we see square root of 25 happens to be a nice number. So we write our answer as 3 square roots of 5 over 5. And we would say we have rationalized the denominator. And rationalized because there's no square root down on bottom anymore. Notice it did force us to put a square root up on top. Seems as though we're okay with that. This is the way people usually want things done. They want the bottom rationalized, not the top. Alright, let's take a look at the next one. We would multiply top and bottom by square root of 10. So that would give us 6 square root of 10 over square root of 100, which is 6 square root of 10 over 10. And then we would go one step further and we would notice that the 6 and the 10 can reduce. You can cancel a 2 out of each of those. So you would write it as 3 square root of 10 over 5. And again, don't think that there's any pattern here. I just picked problems at random. The fact that I have a 3 and a 5 here and a 3 and a 5 there is just a happy coincidence. Nothing special there. Alright, one more of these. We multiply top and bottom by square root of 14. So 14 times 3, calculator says that's square root of 42. And down on bottom, I'm going to write this as square root of 14 squared, because I don't know what 14 squared is off the top of my head, and I don't feel like using my calculator. The good news is I know that the square root of 14 squared is just 14. Squares and square roots are inverses. So I just get square root of 42 over 14. Now, square root of 42, you should look to reduce that, but I don't think you can. 42 can be divided by 2 to 2 and 21, but neither of those are perfect squares. 42 can divide by 3 to 3 and 14, but neither of those are perfect squares. And I think the only other way you can divide 42 is by 7. 7 and 6. So, square root of 42 doesn't have any perfect squares in it. That's the best you can do. Okay, so quick review again. If you only have one thing down on bottom, one little square root, you simply multiply by exactly the square root. If you have more than one thing down on bottom connected with an add or subtract, then you multiply by the conjugate. Told you I was going to use that word again. 2 minus square root of 5. 2 minus square root of 5. The reason we do that is, look what happens down on bottom. 2 times 2 is 4. The middle two are going to add up to 0. We saw that already. Saw it up above. And when I multiply these two, I get minus square root of 25. So down on bottom, that gets rid of all of the square roots for me. I end up with a minus 1 down on bottom. Alright, well now I got to deal with the top. Up on top, I would have 6 minus the square root of 5. Ooh, no, 6 minus 3 square roots of 5. I got to take that 3 and distribute it. So that's 6 minus 3 square roots of 5. 6 minus 3 square roots of 5, just filling in the top all the way. Now I would probably take one more step here. I would divide by negative 1. 6 divided by negative 1 is negative 6. And then negative divided by negative is positive 3 square roots of 5. So you can see this is a nice example of why rationalizing helps. Sometimes when you rationalize, you start with a fraction, you get all done, you no longer have a fraction. Now, truthfully, that's pretty rare, but that's one of the reasons why we do it. All right, let's look at a couple more. This one, we would multiply top and bottom by the conjugate. The conjugate would be 3 plus square root of 7. Alright, this time I'll do the top first. Up on top I have 12 plus 4 square roots of 7. Down on bottom I'm going to have 9 minus square root of 49. Again, when you do the multiplication, the middle two terms add up to 0. That's 12 plus 4 square roots of 7. Divided by, I'm going to do 2 steps in one here. Square root of 49 is 7. 9 minus 7 is 2. Now, important thing, 12 can be divided by 2 and 4 can be divided by 2, so we can divide. If this were a 12 and this were a 5, we would not be able to reduce everything by 2. Since everything can be reduced, we reduce. 6 plus 2 square roots of 7. Alright, last one. The fact that we have a square root on top really doesn't change anything. We multiply by the conjugate. 1 minus the square root of 2. So this is square root of 6 minus square root of 12. And down on bottom we have 1 minus the square root of 4. So that's square root of 6 minus square root of 12 over 1 minus 2 is negative 1. So that's, I would write it this way, I think, square root of 12 minus square root of 6. And then maybe we would say, well, square root of 12 is 4 times 3. So we should simplify that. So that's 2 square roots of 3 minus square root of 6. Now I'm going to throw in one more problem here just because, again, I picked problems at random here, and it came out that the fractions always went away, and I just want to show you that doesn't always happen. Let's say I give you 5 over 6 minus square root of 2. We would multiply by the conjugate, 6 plus square root of 2. We would have 30 plus 5 square roots of 2 up on top. Down on bottom, we'd have 6 times 6, that's 36, minus the square root of 4. So that's 30 plus 5 square roots of 2 divided by 36 minus 2 is 34. Now, here's a good example. It would be very tempting to reduce the 30 and the 34. You cannot. If you're going to reduce, you have to be able to reduce in all three places. I agree that you can reduce a 2 out of these two. You can't reduce a 2 out of that one. So don't reduce that one. That's it. Okay, so like I say, there's a good example to show you that quite often when we rationalize, not all the fractions go away.